This is a parametric problem, meaning that we're describing the motion of a particle along the x in terms of one function dependent on a variable t, which is time, and the motion along the y in terms of a separate function. And then we're asked to evaluate various aspects of this particle's motion, whether it's moving to the left or the right, what the slope of the path is, what the position of the particle is, what its speed and acceleration are, how much distance it covers. All of this given not the x and y position as a function of time, but instead given the rate of change of the x and y position as a function of time. So this is what I consider to be the useful information: definitions of velocity and acceleration, and then a triangle that I hope helps to illustrate all three of the following definitions. The definition of speed as the magnitude of the hypotenuse of the triangle, the definition of slope as the rise over the run of the triangle, and the length of a curve as simply the sum of a whole series of infinitesimal hypotenuse lengths along a curve. So let's jump in. And A asks first whether the particle is moving to the left or the right at t equals 2. Well, the horizontal movement of the particle is entirely determined by the x position and how it's changing. And so all we have to do is evaluate whether dx dt is positive or negative or potentially 0 at the time t equals 2. So we're going to just say motion to left or right is determined by the sign of dx dt at t equals 2. Now we don't even need to use the calculator for this part, even though this is a calculator question, because it's really just saying 2 plus 2 over e to the 2, which is clearly greater than 0, therefore rightward motion. Now what else do they want to know in part A? The slope of the path of the particle at t equals 2. Alright, so here's where it becomes important to make reference to this figure. We have dx dt indicating the x component of the velocity, dy dt indicates the y component, and so dy dx is simply the change in the y component as a function of time over the change in the x component. That's the slope of the particle. So we're going to have to calculate dy dt over dx dt at t equals 2. So let's just write that out. Slope equals dy dt over dx dt, and we're going to evaluate numerically at t equals 2. Now for that we're going to use the graphing calculator, and I've already programmed in the fact that 1, we're in radian mode, and 2nd, we're in parametric mode. And then I've put in the x and y formulas. So now, having put them in throughout the rest of this problem, I just make reference to them using the vars button. And so, for example, to find dy dt over dx dt, both evaluated at t equals 2, note that I can just write, give me the parametric y1 of t, that's the y velocity, and I want it evaluated at 2, divided by another variable, namely the parametric x, and evaluate that also at 2. There's my answer, 3.0547. I'll just say slope is approximately 3.0547. There are no units, so I'm not worried about that. Okay, let's go to part B. We need to find the x-coordinate of the particle's position. You know, now that they mention the x-coordinate, it reminds me that we probably should have included the fundamental theorem of calculus in our description of useful information. So I'm going to put that back in here. Namely, if you want to know a function, let's see. If you want to know a function and its value at x, you just take its value at a known point and add to it the integral from that known point out to x of the derivative of the function. And we just use t as a parameter separate and distinct from x. So that's the fundamental theorem, and that's what we're going to find useful here in part B. Okay, so that means they want x at 4, so x of 4 just equals x at a known point. Now they told us the x and y values at t equals 2, so we'll start from there, x of 2 plus the integral from 2 to 4 of the derivative of x, but they've given us that, dx dt. I can evaluate this numerically as well. First we can put in what this is. X of 2 is given as 1. And so I can evaluate that numerically going back to the calculator. I'll just need to make reference to the integral of dx dt, which is the x1t function. So I'm going to go to the catalog and down to the F section. I want the finite integral. We'll start at 2. We're going up to 4, and our function is x1t. So let's go locate that. And of course we're integrating with respect to t. I'll add to that initial condition that they gave us, namely the position at t equals 2. And my answer is 1.2529. I use that approximate symbol. I think that's all that was required for B. Let's try C. The speed of the particle. So the speed is a scalar value, namely the length of the velocity vector. Again, I've illustrated that here, that we take, just using the Pythagorean theorem, the square of this plus the square of this, take its square root, that gives us the hypotenuse. That's the length of the velocity vector at a particular time. So how are we going to find that? Well, we are going to say that speed equals the absolute value of a velocity vector, which is going to be the square root of of dx dt squared plus dy dt squared. Again, we can evaluate that numerically. At t equals, when did they ask for it? At t equals 4. So I just need to calculate the square root of x1t squared plus y1t squared evaluated at t equals 4. So let's just reference those equations. Again, it's very useful to put these equations in just once so that you can then reference them each time you need to. We need that squared. Actually, we need that squared at t equals 4. Let's back up. Okay. Now we need that squared, and then we need to add to that the y squared value. So we need to evaluate that at t equals 4, and then we'll square that. That's what we're looking for. And again, don't be confused. x1t, we chose to store the dx dt equation in. Similarly for y1t. So this really says dx dt at 4 squared, dy dt at 4 squared. And we get 0.5745. Okay. Now they also want the acceleration vector of the particle. So acceleration, that's the second derivative of x, second derivative of y. Notice they asked for the vector, not the magnitude of the acceleration, which would be like asking for the speed instead of the velocity. They just asked for the vector. So we're going to take the second derivative of this at t equals, is it 4? At t equals 4. And then we'll take the second derivative of this at t equals 4. Okay, so let's just write that out. Acceleration equals, I'm using these so-called angle brackets because that's how I think the AP exam readers are most comfortable with vector notation. You could use I hat and j hat notation as well, or x hat and y hat notation. But if those things don't mean anything to you, don't worry about it. Just stick with what we've got here. We know this. Okay. And we'll just say evaluating numerically at t equals 4. Acceleration is approximately equal to, again, this is the third or fourth time we've made reference to the already input equations for dx dt and dy dt. Now we're going to have to take in derivative of that, because the derivative of the velocity equation is the acceleration. It's the second derivative of the position equation. So we need in deriv from the catalog. We need to take the derivative with respect to time. I'm still in parametric mode, of course. And the equation we want to grab is the dx dt equation, which we stored in x1t. And then we want to evaluate it at t equals 4. Then we'll separately handle the y. But first this. We've got negative 0.0411. And now let's do the y. Same situation. We go to the catalog. We want the deriv. We're using t. We're taking a second derivative by taking the derivative of the first derivative. And that first derivative function, again, we stored in y1t. That's all we need there. We're evaluating that at t equals 4. And we've got 0.9893. All right, one more section to go. Carve this out. Let's talk about d. The distance traveled by the particle. So, distance traveled is simply the length of the curve as the particle goes from t equals 4 to t equals 2 to t equals 4. Distance traveled is 2 to 4 Again, it's really just the length of the velocity vector integrated over time. And so we're going to say, evaluating numerically, distance is approximately, last time we'll use this, so we're going to integrate and we'll start at 2 and we'll go on to 4, and that's going to be quite a long and involved expression. Let's put that in. It's going to be the square root function, and we're going to do that for our y vars. Our dx dt, that has to be squared, plus our dy dt. And that also has to be squared. Our variable of integration is t. Away we go. It's thinking. 0.6509. And there were no units, so we'll just leave it unitless. Again, I hope this gives you a better sense of how to handle parametrics.